Hello everyone, welcome to Rasaayana Institute of Sciences. So in this video we are going to discuss about concept of hybridization. So how hybridization is going to be helpful for organic molecules and what are the standard logics as well as what are the conceptual logics to identify the hybridization. Clearly we are going to discuss in this video. Okay, so what is hybridization actually and how this hybridization is going to be helpful in organic molecule, not only in organic molecule, even they are also helpful for inorganic molecules. Okay, let's see. So hybridization is nothing but intermixing of atomic orbitals. So I'm intermixing atomic orbitals to give hybrid orbitals. So atomic orbitals are get combined together and forms a hybrid orbitals is nothing but hybridization. And very important thing is how many atomic orbitals we are mixing, same number of hybrid orbitals you will get. Suppose if I am intermixing two hybrid orbitals I want to get. So I am going to mix two atomic orbitals and you will get two hybrid orbitals. Okay. Suppose if I intermix two, you will get 2. Now I am intermixing 3. You will get 3 hybrid orbitals. So number of atomic orbitals is equal to same number of hybrid orbitals, that is called hybridization. Suppose generally we know carbon atomic number is 6 and electronic configuration is 1s2, 2s2, 2p2. Okay. So if you write electronic configuration clearly for outer orbital, this is 2 electron, 2 electron, 2 electron. Only this I am writing because it is a outer orbital. Okay. So outer orbit having s orbital as well as p orbital. Now this is a ground state electronic configuration. If it is excited, you will get total 4 free electrons. So one s atomic orbital, p, and this is p, x, y, and this is z. So now total 4 atomic orbitals are ready to intermix for carbon. And whenever if it is combining together, they will undergo hybridization. So right now, if I take carbon, suppose one s orbital, and here I am writing px orbital, this is py orbital, and this is pz orbital. So if any one particular carbon, if they intermix these four atomic orbitals are combining, now on that time you will get 4 hybrid orbitals like this. This is 1, this is 2, and this is 3, and this is 4. So they are called 4 hybrid orbitals, and this all are 4 atomic orbitals. One s orbital, 3 p orbitals are combining. Total 4 is combining, you will get 4 hybrid orbitals. Here 1 electron, 1 electron, 1 electron, and this is 1 electron. So total 4 free electrons are present. Now this orbital is sp3 hybrid orbital, sp3 hybrid orbital, and here also sp3 hybrid orbital. Total 4 hybrid orbitals are present on this carbon. So you will get 4 atomic orbitals responsible for this one. Suppose same molecule, if I take one s orbital, px orbital, and here py, one more is there. So this is orienting in z axis, this is pz. Now what I am saying is, out of these 4 I would like to intermix only 3. Only 3 means in which one will be definitely s orbital and one will be px py, px pz, or py pz. Any one p orbital is not involving in hybridization. So on the time one s orbital, 2 p orbitals I am contributing, only these 2 are contributing, these 2 are not involving in hybridization. So on that time what happens, see, only 3 hybrid orbitals you will get. This is 3, 1, 2, 3. Now you will get 1, 2, 3. 3 hybrid orbitals with 3 electrons. So this orbital is not involving in hybridization. This orbital is nothing but a real orbital. Okay, plus, and this is minus. It is also called unhybrid orbital. This is real orbital, also called unhybrid orbital. Okay. So now last possibility, s orbital is combining with, this is px, py, and this is pz. So in this I would like to intermix only 2. So carbon undergo intermixing only 2, carbon may undergo intermix with 3, and this is 4. So if they undergo two intermixing, now what happens, see, you will get two hybrid orbitals. Here one electron, one electron. So this is sp, and here also sp. So three intermixing atomic orbitals responsible to give three hybrid orbitals, sp2, sp2, sp2. Okay. So now on this sp carbon, two atomic orbitals are not involving in hybridization. That would be py and pz. Py and this is pz. Now I can say these orbitals are nothing but real orbitals. Now the question is, only hybrid orbitals are responsible to give sigma bond. Unhybrid orbitals, this is unhybrid orbital, also called real orbital. Here also real orbital. Only real orbital is responsible to give pi bond. So because real orbital undergoes sideways overlap is very weakest overlap, that is responsible to give pi bond. So intermixing of atomic orbitals responsible to give hybridization. That hybridization may be sp3, sp2, sp for carbon. Clear? So generally carbon can show only three possible overlaps. It might be either sp3, sp2 or sp. Okay? Right. Next. See, suppose if I take alkane CH3 I am using now. Okay. So in this particular molecule, this carbon hybridization is sp3 I am saying, and here also this is sp3. Suppose if it is sp3, you can also calculate by using one general logic. I will explain that logic. Right now remember, this carbon is sp3. So if it is sp3, 4 hybrid orbitals are present. Here 1, 2, 3 and this is 4. Total 4 electrons are present like this. This carbon, it is also sp3. Now it is overlapping like this, 1, 2, 3 and this is 4. So here 1 electron, 1 electron, 1 electron, 1 electron. So these all are sp3. sp3 and here carbon overlap is sp3 and here also it is sp3 and here sp3. Every hydrogen having one s orbital, that s orbital will overlap here. So after overlap, see this particular carbon sp3 carbon having sp3 hybridization between these two carbons, and these all are hybrid orbitals. So sp3 one overlap and one more overlap is sp3s overlap. sp3s total 1 2 3 4 5 6 sp3s and only one sp3 overlap. So this is for a single bonded carbon. Suppose if I take a double bonded carbon, now what is the hybridization of this carbon? sp2. We know if carbon having sp2 hybridization, generally 3 atomic orbitals are intermixing and 1 orbital is left over as a unhybrid orbital, also called real orbital. So I can write like this. This is one hybrid orbital, one more hybrid orbital, here one more hybrid orbital for sp2 carbon. Okay, and every sp2 carbon carry one real orbital. That is this one. This is a real orbital. It may be a px, py or pz, any one you can take. Now here 3 electrons I am writing. Okay, and I am writing this carbon, second carbon, one sp2, other sp2, one more sp2, and this carbon also exhibits one unhybrid real orbital. Okay, now here they may carry one electron, here one electron. Now every sp2, one unhybrid real orbital is here, they carry one electron. And this carbon carry 2 hydrogens, here one hydrogen and here also one hydrogen, and here one hydrogen and here also one more hydrogen is left. And these real orbitals are not involving in hybridization. They are also called unhybrid orbitals, pure orbitals, many names are there. So these unhybrid orbitals undergo sidewise overlap. This sidewise overlap is responsible to give pi bond. Half pi bond above, remaining half pi bond is completely below. So I can say this is sp2, this is sp2 and here also sp2, here sp2 and here s is there. So total 2 different overlaps are possible. sp2, 1 and here remaining sp2s overlaps are 1, 2, here 4 hydrogens are present, I can say 4. So here only sigma bond is present there is no pi bond, but here sigma bond and pi bond is there. Pi bond formation always takes place by sideways overlap between two real orbitals. That is the concept. Okay, and finally I would like to explain for a triple bond, carbon-carbon triple bond, hydrogen. This is sp and here also sp. Every carbon, two atomic orbitals are involving in hybridization, remaining two will be exist as a real orbital. So I can write like this. See, this is one sp, here one more sp. Now two real orbitals are present here now. This is one real orbital, here one more real orbital. For second carbon, it is sp and here also sp. And see, this sp carry one electron, here one electron. This sp carry one electron and here one more electron. So now this overlap is sp overlap. This might be either py, pz. You can take either px, pz also. Okay, and on this carbon, two real orbitals are available, py and this is pz, and here also two electrons are left. Okay, and this carbon carry one hydrogen. This hydrogen overlaps here with s orbital. Here also remains same. Now this py undergo. See, this is py. You can take this is py and this is pz. This is pz and this is py. Here py, pz. So py overlap sidewise. Pz overlap sidewise. And here also same. Py overlap sidewise. Pz overlap sidewise. Pz sidewise. So total how many pi bonds? Half pi bond. And here also half pi bond. Total two pi bonds are present. So one sigma bond and two pi bonds are present between this. So the question is, the type of overlap exhibits between these two carbons is, okay, so that is sp only. Between these two carbon, sp overlap is observed, that is only one. And this carbon having only one hydrogen, that overlap is sps, and such overlaps are, two will be there, that is two sps overlaps. So this is the conceptual knowledge to find hybridization existing between two specific species. Okay, so one will be sigma bond species, other will be pi. So just rewinds once. The intermixing of atomic orbitals to give or redistribute to give equal and similar energy, hybrid orbitals, is called hybridization. So how many hybrid orbitals are formed depends upon how many we are combining. If you are getting 2 means 2 I am intermixing. Generally carbon ground state, excited state 4 atomic orbitals are available. Carbon will give generally 3. sp3, sp2, sp. Okay. Now 4 I am intermixing. In these 4 atomic orbitals I am intermixing. S orbital, 3 p orbital. Okay. Now here I am intermixing 3. Here I am intermixing 2. If I intermix 4, there is no leftover atomic orbitals. So that's why here I am not written any real orbital. Here one real orbital is there on one carbon. This is a real orbital. And here two real orbitals are present. You can write like this. Every real orbital also carry one free electron. Here free electron, here also one free electron. This is a conceptual knowledge. See, this carbon having sigma bond, sp3 overlap. On this carbon there is no real orbital. Already just now explained. sp2 carbon having one real orbital. sp2 carbon having 4 real orbitals. This carbon 2, this carbon 2. So always real orbitals are pure orbitals. If they undergo sideways overlap, they are responsible to give pi bond. So here half pi bond above, half pi bond below, finally only one pi bond. Okay. Now next, see the standard logical approach to find hybridization of organic molecule. See this. So if you want to calculate hybridization of any molecule, remember number of sigma bonds plus number of localized lone pair. So sum of these two will give one number. If that number is 2, if that number is 2, hybridization is sp. If that number is 3, hybridization is sp2. If that number is 4, hybridization is sp3. If that number is 5, for all elements in the form of molecule that I am writing, it would be sp3d. If it is number is 6, hybridization is sp3d2. That is the concept. Okay. Remember, number of sigma bonds plus total number of localized lone pairs will give this number. So based on that, you can calculate hybridization of a given molecule. So one example I will show. Just concentrate. Suppose see methane. I am writing methane. Methane can be written like this. Carbon having hydrogen, hydrogen, hydrogen like this. Total number of sigma bonds are 4. 1, 2, 3, 4. Logical approach, 4 sigma bonds are present. Hybridization is sp3. Now, what is the hybridization of this carbon? sp3. Like that we can find. Suppose, if I take ethane, CS3 and here CS3. Carbon having hydrogen. This carbon also having 3 hydrogens. Now, around this carbon sigma, sigma, sigma and sigma. And this carbon already sigma I written left side. If you concentrate this carbon having 1, 2, 3, 4. So 4 sigmas are there, sp3 hybridization. Same this carbon also 4 sigmas, sp3 will be the hybridization. So I can say simply 4 sigma, 2 carbons bearing sp3. So this carbon sp3 and even right side carbon is also sp3 hybridization. Right? Suppose if I take alkene, carbon-carbon double bond, and we know we can write like this. Carbon-carbon double bond, write down 2 hydrogens like this and 2 more hydrogens like this. It is sigma, sigma, sigma. Sigma and this is sigma. So while calculating hybridization for any reference atom, only that reference atom surrounded sigma bonds has to be taken as a total number of sigmas. So this carbon carry 1, 2, 3. Total number of sigma bonds are 3. So I can say it is sp2. Right? And remember, don't think like this, sir. This sigma bond already counted toward this side. Then can I consider this sigma toward this carbon or not? Yes. Because they are overlapping, there belongs to 2 carbons. So I can say this carbon also having 3 sigmas, then hybridization is sp2. Now, total number of sigma bonds are 3 sigma bonds around any reference carbon. Now hybridization is sp2. So I can say this carbon having sp2 hybridization and here also having sp2. Clear? Now, next see this. I would like to take one triple bonded carbon. See this, carbon-carbon triple bond. Okay. Now, this carbon having number of sigma bonds are here left side 1 sigma, middle sigma, this is 1 more sigma. So this carbon having 2 sigmas. So I can say 2 sigma, then hybridization is sp. So this carbon is sp and here also this carbon is xp. Just count total number of sigma bonds around the carbons. You will get the answer. Suppose I am taking this carbon, hydrocarbon molecule. This is called alene, propadiene. Now, around this carbon, sigma, 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 sigma is there. Suppose if you consider this carbon, 3 is there. So 3 means sp2, 2 plus 1. This carbon is sp2 and this carbon having only 2 sigma bonds, so I can say sp. Okay. Suppose if I take benzene double bonded carbons. Now, around this carbon 1 hydrogen is there, here also hydrogen and here also hydrogen is left. Hydrogen, hydrogen and here hydrogen. So you take any one carbon in benzene. Suppose if I take this carbon in benzene. Okay, this carbon carries sigma, sigma and this is sigma. So total 3 sigmas are present, hybridization is sp2. So benzene hybridization is sp2. You take any molecule if they have double bond. If one carbon sharing double bond, on that time hybridization is sp2. Okay. Suppose if I take any halogen, suppose chlorine is given. Around this chlorine, 1 sigma bond, 3 lone pairs are present. This chlorine carry 1 sigma, 3 lone pair. So then hybridization is what? 4, sp3. And even I can take alcohol. This is OH. Now, around this oxygen, 2 sigma bonds, 2 lone pairs are present. Total 4. So now hybridization of this oxygen is sp3. Okay. Suppose If I take any carbonyl group, C double bond OH, this is carbonyl group, here lone pair is present, and if you want to calculate hybridization of these two, here one sigma bond, two lone pair. Now number is 3, 3 means sp2. Oxygen hybridization is sp2. Okay, now see, if any one particular element in which conjugation is present, see this lone pair is conjugate to this double bond. If it is conjugate to double bond, one lone pair is involving in delocalization, one lone pair should not be considered in calculation of hybridization. So I can ignore this lone pair. One lone pair you need to ignore, remaining 3 you need to count. Here sigma, sigma and one lone pair. Only one lone pair, 2 sigma should be considered. So here 1, 2, 3. Then hybridization is sp2. This is not sp3. Don't consider like this. If any heteroatom conjugate to double bond or triple bond, one lone pair is involved in delocalization, that we need to ignore. Leftover lone pairs and sigma bonds will give one number. That number will give either sp2, sp3, sp3, etc. Okay. So I will give one more example. See, CH3, CH2 and here nitrogen carry one lone pair of electron. Observe clearly, nitrogen having 2 hydrogens. Right side one hydrogen, left side one hydrogen. Sigma, 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 one lone pair. Total 4. Hybridization is total number of sigma bonds and lone pair. 1, 2, 3. So now 4, hybridization is sp3. Apply the same nitrogen in this particular case. Carbon nitrogen. This is called ene plus amine, enamine. Now I am taking this lone pair, but what happens, see, nitrogen lone pair conjugate with this double bond. So it will involve in delocalization. On that time, one of the lone pair present on heteroatom or total family, whichever lone pair is involving in delocalization, that will be ignored. So I am ignoring this lone pair, I am considering only sigma bonds. Now it will be 3, then answer is sp2. It is not sp3, it is sp2. Okay, next. Suppose if I write this molecule C double bond OH, and if you want to calculate hybridization of this oxygen, see this. Carboxylic acid oxygen involving in delocalization like this. Only one lone pair is involving. So I can consider one sigma bond, other sigma bond and one lone pair in calculation of hybridization. So take 2 sigma bonds and one lone pair. Now total will be 3. So total 3 means hybridization is sp2 like this. Right, see this. Suppose if I write any negative ion, this is -1. -1 indicates that yet this oxygen carry already 2 lone pairs. Already 2 lone pairs. Generally, every oxygen carry 2 lone pair. -1 means one extra lone pair. Is this lone pair involved in delocalization? No, because there is no conjugation involved in this one. Now here 3 lone pairs. 3 lone pairs plus 1 sigma. 1 sigma bond is present. Total 4. 4 means hybridization is what? sp3. Now this oxygen hybridization is sp3. Right? Suppose if I write CH3NH-1, then how to write this structure? I can write like this. CH3 nitrogen and here hydrogen. Nitrogen having one lone pair. Already existing lone pair is 1. -1 means one extra lone pair. This is a real structure. This is called Lewis dot structure. Okay. Now, if you want to calculate hybridization around this nitrogen, sigma, sigma, 2 lone pair. 2 lone pair, 2 sigma. Total 4. 4 means what is hybridization? sp3. So now this nitrogen hybridization is sp3. Because this lone pair not under conjugation, not involved in delocalization. Now same molecule, I would like to write like this. Here -1. If you are getting -1, carbon-carbon double bond and here lone pair, and this is one more lone pair. Okay. Now see the difference between these two species. Here negative ion not involved in conjugation, but negative ion involved in conjugation. And we know that -1 means 3 lone pair, one extra lone pair. Out of these 3 lone pairs, one lone pair involved in delocalization. So I would like to consider one sigma, 2 lone pairs in order to calculate hybridization. Total will be 3. Sigma, lone pair. 1 sigma, 2 lone pair. Total 3. 3 means hybridization is sp2. See, here O minus, here it is also O minus. These two species in which O minus ion not having same hybridization. It is sp3, but here it is sp2. Okay, so same in this case with n minus ion. See the difference. In this n minus 1, sp3, but here see, this molecule I can write like this. CH2 carbon double bond, here nitrogen, one hydrogen, here lone pair, and here one more lone pair. One is involving in delocalization, 1, 2, 3. 3 is there, so hybridization is sp2, like that. Everywhere same concept. When negative charge is present on any element, if it is involved in delocalization, one extra lone pair. Okay, so CH3, CH2, and here nitrogen carry -2. Then what is the hybridization of that nitrogen? You can write like this: CH3, CH2, nitrogen carry extra 2 lone pairs. Already nitrogen having 1 lone pair. -2 nothing but 2 extra lone pairs. Now 1, 2, 3, 4. So 4. 4 means hybridization is sp3. Suppose if it is involved in conjugation, if nitrogen is under conjugation, you can guess like this. Here -2. Then what is the hybridization of this nitrogen? You can write like this: carbon double bond, nitrogen carry here 1 lone pair, 2 lone pair, 3 lone pair. Out of 3, see -2 means 2 extra. Already 1 lone pair is present, we know very well. Now this lone pair involved in delocalization, ignore this lone pair, consider 2 lone pairs, 1 sigma bond. Total will be 1, 2, 3. 3 means hybridization is sp2. That's it. Now see this example. This is called phenoxidine. Suppose this is phenol. First you take phenol. Phenol, 1 lone pair involving in delocalization. So sigma, 1 lone pair. Total will be 3. 3 means sp2 will be the hybridization. Only 3, 1 lone pair, 2 sigmas are present on phenol. 1 lone pair involved in delocalization. Now if I take O minus 1, O minus 1 means already oxygen having 2 lone pairs. This is 2 lone pair. -1 means 1 extra lone pair. Now this 1 is involving in delocalization. Then count remaining leftover, which is not involving in delocalization. 1, 2, 3. So total is 3. Hybridization is sp2. Phenoxidine, phenol having same hybridization. Okay. Now, so this is called tetrahydrofuran. THF. Tetrahydrofuran. 1, 2, 3. So no conjugation, hybridization is sp3. Now here conjugated THF, it is under conjugation. Now 1 lone pair involving in delocalization. So sp2 become sp3. So even though 2 sides, if conjugation is present, don't think that 2 lone pairs are involved back to back. Suppose see, 2 lone pairs are present. This lone pair involved in delocalization with this side. So don't think like this. This is involved this side, this is involved this side. No. If it is under conjugation, we need to ignore only 1 lone pair. Consider this lone pair involved in delocalization. Consider 1, 2, 3. Only 3 will be considered. If I consider 3, that is sp2. Furan. This is called furan. Furan hybridization is sp2. Okay. So same. Pyrrolidine. Now here nitrogen having 1 lone pair. Now 1, 2, 3. 3 is there. sp3 will be the hybridization with lone pair. Total 4. Okay. Suppose if I put any double bond over here, like this, if I put This hybridization is still sp3 only because it is not involved in delocalization. No conjugation, no delocalization. Now if I write like this, now this lone pair involved in delocalization, now hybridization is sp2. Even in this case also hybridization is sp2. Here double bond hybridization is sp2. So when heteroatom lone pair, if it is conjugate to any double bond, one of the lone pair involved in delocalization, that we need to ignore. Okay. Suppose if I take pyridine, this is pyridine. Right? Here one lone pair is there, it is not involved in delocalization, already 6 pi electrons are involving in delocalization. So now this lone pair is localized. This is localized lone pair, sigma, sigma, one lone pair. So this nitrogen carry 2 sigma bonds and one lone pair. I can say simply hybridization is sp2, pyridine. This molecule name is pyridine. Pyridine nitrogen hybridization is sp2. So like that we can calculate many hybridations of a molecule, but concept is remain same. Every time when any heteroatom having -1, -2, -3, whatever it may be, if it is under conjugation, one lone pair we need to ignore. Suppose if there is no conjugation, that extra lone pair we need to include in hybridization. That will give one number. Based on that we can write hybridization of a selective atom. Okay. So even for aromatic compounds, anti-aromatic compounds, homoaromatic compounds, non-aromatic compound, this concept will be most helpful. Okay, just make a short revision once. See this, hybridization is intermixing of atomic orbitals to give molecular orbitals. How many we are mixing, you will get same number of hybrid orbitals. Carbon as a reference element I taken because carbon is a major constituent in organic compounds. Carbon, if all orbitals are intermixing, only 2 intermixing, 2, 3 intermixing, 2 intermixing. Now this orbital is a real orbital. Here 2 real orbitals are present. So they are atomic orbitals, they are hybrid orbitals. I am intermixing 1, 2, 3, 4. 4 atomic orbitals. Now here see sp3, 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 sp3. So I can say 4 hybrid orbitals like that. Next. So I am taking alkane, carbon-carbon overlap. In this there is no real orbital. Here one real orbital on this carbon, one more real orbital on this carbon. Every real orbital is also called unhybrid orbital, also called pure orbital. This carbon having 2 pi, 2 real orbitals, etc. Right? Next, see few examples I given. It is a shortcut for your IIT mains examination, advanced examination, even for Neet examination, and even for advanced level chemistry. This concept is most helpful because many areas are tied up with hybridization only. If you are very familiar with hybridization, concept of acidity, basicity, reactivity, okay, chemical reaction participation, pi bond participation, sigma bond participation, many organic reactions you can write very easily. Okay. So shortcut for writing hybridization of any organic molecule is hybridization is equal to number of sigma plus number of lone pairs. Okay. So I given one number. If you calculate this two, based on the number I am writing hybridization. Around carbon 4 sigma bonds are present, sp3. If you are getting 4, sp3. Here see 4 means 3 plus 1. 3 p orbitals, 1 s orbital. Like that you need to count. Okay. Same way. Here I given sigma and here pi. Next, if you consider triple bond having sp, around this carbon 2 sigma bonds are present, sp. Around this carbon 3 sigma. Benzene carbon is sp2, and from here onwards be careful. This chlorine carry 1 sigma, 3 lone pair. 1 sigma bond plus 3 lone pairs are present. That's why hybridization is 4. Number is 4, sp3. But same oxygen, 2 lone pair, 2 sigma, sp3. Here 2 lone pair, 1 sigma, sp2. And here also same. But remember, if any lone pair conjugate to pi system or conjugate to cation, on the time, one lone pair we need to ignore. Around this oxygen, 1, 2, 3. I am counting, see. 1 lone pair, 2 sigmas I am counting. I am not counting this lone pair. Because this lone pair involving in delocalization. Here there is no delocalization. So ignore this. count only 3, you will get sp2. And here also same, this 2. And go through this case. How to write a Lewis dot structure if they given a pure anionic form or cationic form. -1 means already oxygen carry 2 lone pair and this is one extra lone pair. So there is no delocalization. 1, 2, 3, 4 sp3. And here also same. 2 plus 2, 4. O minus 1 extra. That extra is involving in delocalization. Consider 2 lone pair, 1 sigma. These points are very, very helpful, especially this classification. If it is under conjugation, ignore 1 lone pair. -2 means 2 extra lone pairs, already 1 lone pair is existing. This is already existing lone pair on nitrogen. 2 lone pairs nothing but -2. Suppose Cl -1 if I write. Cl -1. Chlorine carry 3 lone pairs already. And -1 means 1 extra lone pair. Like that we need to imagine. If it is delocalizing, if it is under conjugation, delocalizing, ignore 1 lone pair. And here also same. Phenol, phenoxidine, furan, heterocycle compounds and pyridine, everything I explained. If any lone pair is under conjugation, it will involve in delocalization. If lone pair is not under conjugation, see it is not conjugate. Sigma bond, sigma bond. So now it is a free lone pair, sp3. Okay, so that is about conceptual and standard logical approach on concept of hybridization, which will be helpful in most of the organic molecules. Try to prepare well and try to subscribe our channel. Such type of videos we are going to upload every day. Try to share this video to your friends so that we are going to upload every day new videos, and that will be given in the form of notification so that you can get clarity on your concept. Thank you for watching this video.